It's a great pleasure to introduce and to have amongst us Joel Kamnitzer, who is one of the world's experts in tying the representations of groups into various bits of exciting geometry and all coherent and functorial. He is, I think, won every prize he can, and quite justly so. So he's been a Sloan Fellow, a Stacey Fellow, and any other things. And he's been the professor at the University of Toronto since the early 2000s. So it's a great pleasure, and you'll tell us about cacti.
Thank you, Jacques, for the introduction invitation. I guess I'll take that answer. That's okay. Okay, so welcome to those online and in the room. So I'll be speaking today about cactus groups and monodromy of, well, we'll see what it is monodromy of soon. So I'm going to begin by discussing this moduli space. I'll denote it Mn. So it'll be a moduli space of points on P1. So for this talk, we'll work just over the real numbers. So we consider the space of just configurations of n points on RP1. So RP1 is R union infinity. So we each have a circle. Sorry, and I said n, but I meant n plus 1 points. So here's n plus 1 points on a circle. So that space of n plus 1 points on a circle, if we require that the points be distinct, that's the same as considering, well, n plus 1 points on P1. Then we have to take away the fat diagonal, take away the locus where Zi is equal to Zj. And then we mod out by the automorphism group of P1, which is the group of 2 by 2 matrices PGL2. And PGL2 acts on P1 by this fractional linear transformations AZ plus B over CZ plus D. Using this action, we can turn one of the points to be infinity. So we just make one of the points be infinity using that action. And then we just get n points on the real numbers, again, mod minus the locus where they coincide, minus this fat diagonal. And what's left over from PGL2 is just a two-dimensional group of R cross R, where the first factor acts by scaling and the second factor acts by translation. So simultaneous scaling and translation of these endpoints in R. So that would be a kind of, well, boring space in the sense that it's disconnected and all the connected components are contractible. So to make the space more interesting, we're going to compactify it. And how do we compactify it? It's a special case of a general construction due to Deline and Mumford. Although in the case where we're genus 0, which is what we're talking about because we're dealing with P1, in this genus 0 case, it's been studied by many, many people and has a much simpler description. We're going to define this smooth compactification. So in this compactification, what we do is rather than just have endpoints on a single circle, we allow our circle, our curve, to degenerate to these nodal curves where we have multiple irreducible components and allow the marked points to be distributed among these components. So a point of this moduli space that we're studying is one of these stable nodal genus 0 curves with n plus 1 marked points. So genus 0 just means that the graph of the components is a tree and each of the components is a RP1. Nodal just means that at every point we just have two RP1s meeting. And the stable here, that means that the automorphism group of this is trivial, or finite in this case implies trivial, which means that every irreducible component has at least 3 marked or special points. So here's 2 marked points, 2 special points. So to get a feel for this moduli space, let's take a look at some examples. So let's take a look at n equals 2. N equals 2 means 3 marked points. There's this shift, which is kind of convenient later. That's why I have this n plus 1. So n equals 2, that means we have 3 marked points. And what do we do when we have 3 marked points? Well, we make one of them infinity. Then, as I mentioned before, we still have scaling and translation. So using translation, we make one of them 0. And then using the scaling, we make the last one 1. So things are kind of boring because we can specify exactly what those 3 marked points are. So the space M2 is just a single point because there's only one such configuration of points on P1 because of our action of PGL2. So to get something more interesting, we go to n equals 3. There we are. So if we take n equals 3, well, we can again set the first three marked points to be 0, 1, and infinity. And then we have a fourth mark point floating around, which I've marked as Z. And this fourth mark point floats around. And when it starts getting too close to one of the other three marked points, it enters onto a separate component with one of those marked points. So as drawn in the picture, we allow ourselves to produce these configurations where we now have two irreducible components. So this marked point's gotten too close to this one, so they've gone off on their own separate irreducible component. Excuse me. And in this way, on the other hand, that's the only thing that can happen because of this condition of stability, because the graph is a tree and because each one has to have at least 3 marked or special points, there's nothing else you can do with 4 marked points besides such simple configurations. So for that reason, all we have is the original smooth guys where we just have 4 distinct points and then 3 special extra points where these marked points have come together. So the whole space is therefore a circle. So the whole space is a circle given by this fourth point moving around, interacting with this guy, going off on their own, then continuing here, then going here and getting off on his own, and then continuing here, then going here and going off on his own, and then continuing here. And so it's a circle which we think of as glued together from 3 intervals. The intervals correspond to these cyclic orders of these 4 points. So maybe I'll just emphasize this 1 second. So if I take this locus where I have just the 4 points on the circle, and I remember them in a cyclic ordering, well, there'll be 4 factorial orderings, 3 factorial cyclic orderings. Because of this group, PGL2R contains the element inside of the scaling, contains the element -1, that's going to actually reverse the cyclic ordering. So we end up with 3 factorial over 2 components. So these are the connected components of the smooth locus, or of the open set. So these 3 factorial over 2, that's 3. And those 3 intervals drawn here. So that's the space M3. Please let me know if anyone has any questions, either in the room or in the virtual audience. Okay, so let's go on to see what can happen when n is 4. So n is 4 means we have now 5 marked points. We have 5 points on the circle. And now a little bit more interesting stuff can happen. Again, we have a generic sort of locus, the open locus, where we have these 5 points just on the circle as distinct points. And then what can happen is a group of 3 of them can get together and get onto their, so these 3 guys here start coming closer and closer together. And these 2 guys kind of come closer together at the same time. Then this curve can separate into 2 curves, bubble off of the guy here with 3 marked points here and 2 marked points here. And then that's not all that can happen, because then these 3 guys themselves, they might, these 2 decide they might like each other more than this guy, and they go off on their own component like so. So we can have configurations like that. And that's basically all that can happen. So if you think about it carefully, you'll see that yeah, you can see the mouse here, I guess. You can see that this is the this locus here, where I have the 5 distinct points on the circle. There's 5 different ways in which it can separate out like so. So there's 5 different ways this can happen. And then for each of those guys, there's sort of 2 different ways this can happen. And if you imagine that part of the space, you'll get a pentagon. So the closure of this locus where we have some particular cyclic ordering gives us a pentagon. And the entire space is then made by gluing together 12 of these pentagons. So this 12 number, again, comes like as so. It's 4 factorial, that's the cyclic orderings. And then I divide by 2, that's because of this -1 element in my group PGL2, and that's 24 divided by 2. So the entire space is a two-dimensional space, a topological surface, which is made by gluing 12 pentagons together. So it's a little hard to picture, but surprisingly, it's possible to draw a picture of the entire thing. And so that's 12 pentagons. And the little arrows around the boundary tell you exactly how to glue it. Maybe I didn't quite draw enough arrows. This will see one that connects the top edge and the bottom edge. So it's a topological surface of Euler characteristic -3. Another way of saying the same thing is you take a torus, usual like donut, and take the connect sum with 3 RP2s.
Okay.
Anyway, there's many different ways of thinking about this space, but there it is. So the white part is not part of the space. Yellow part is the space. So again, each of these regions inside, each of these pentagons, they correspond to a particular cyclic ordering of those points 0 up to 4, modulo this flip operation. Okay, so in general, the space Mn, defined this way, it's a smooth compact manifold, often non-orientable, and it's of dimension n-2. And you can build it by gluing together these generalization of these pentagons, which are called associohedra drawings. So if we would glue together these n-1 factorial over 2 associohedra, and we get this space Mn. I didn't really tell you how to glue them, but there is some way. Another way of thinking about the space is you could start with this space, the projectivization of Rn mod R. Another way of saying that is, if you just start with P1, this is slightly different. So this projectivization of Rn mod R, that's like the naive thing you would do where you allow the points to coincide. And then to make our given R space Mn, we construct it by doing an iterated blow-ups construction along the hyperplanes of this braid arrangement. I won't really explain what that means because that would take too long. Okay, so that's a space Mn. Are there any questions about it? So it's like maybe a slightly involved description of a space, but I'm trying to convince you it's not like a extremely complicated thing. It's just a nice, smooth, compact manifold, and we have very nice hands-on combinatorial description of it. So why am I interested in the space? Largely because I'm really interested in this other thing called the Cactus Group. So let me explain what this Cactus Group is. So Cactus Group is something also very hands-on. You could teach it in the elementary group theory class. So it's just a group with that presentation. So it has n-2 generators. Maybe I'll just do an example while we're seeing it. We could have generators like, say, if in S4, we would have 6 generators, S12, S23, S34, S13, S24, and S14. So the generators correspond in this case to intervals between 1 and 4. 1 and 4, and anyway, some interval is inside there. So those are the generators. All the generators square to the identity. So it's a group generated by involutions. And then there's 2 relations. So the 2 relations are that if the 2 intervals are disjoint, for example, S12 and S34 are disjoint, then they'll just commute. And the second relation is that if one interval contains the other interval, then the outer interval, the one for the outer interval conjugates the one for the inner interval in the way that is most natural if you think about it. So it's kind of supposed to be drawn in the picture there. So you have an outer interval. Let's say this is our outer interval, and you have an inner interval that's here, and then the conjugation of the outer guy by the inner guy flips the inner guy inside the outer guy. And in terms of formula, it's Sij SKL is Si plus J minus L, I plus J minus K Sij. Anyway, so it's a slightly weird formula, but there's an example. So like, for example, this 1,2 is getting flipped inside 1,4 and becoming 3,4. Another example would be S14, S13 is S24, S14. Okay, so it's just a group with this presentation. So it's not a finite group, it has a finite presentation, but you can start putting together these generators, you'll get really many things. One nice thing about this group is it has a map to the symmetric group. So symmetric group is a group just of permutations of n objects. And Sij under this map corresponds to the permutation I'll call Wij. So it's a permutation which takes the section of the, so I draw a permutation as in this diagram to show sort of where things are sent to. So in the permutation Wij, it doesn't do anything with 1 up to I, and then between I and j, it completely reverses that interval. And the latter ones, they stay the same as well. So it just completely reverses that interval, and that sort of explains why where this relation kind of comes from. So we're thinking of this generator Sij as some kind of flip of the stuff between I and j.
So in terms of configurations of points, you're sort of moving all the points together, then taking them through a bubble and then moving them outwards?
Well, we'll see that in about 5 minutes, yes.
Oh, okay. Sorry.
You're anticipating well, yes. The kernel of this homomorphism of groups I call the pure Cactus group. Here's just a quick example. If we did n equals 3, so that we only have, well, 3 generators, S12, S23, and S13, then this element, S13, S12, S23, S12, that thing goes to the identity in the symmetric group because S12 goes to this thing. So if we probably people may have seen this as this Radameister 3 picture. So if you take this S12, S23, S12, it'll be mapped to this element of the symmetric group, which is the same as W13. So in the symmetric group, W13 is the same as W12, W23, W12. And therefore, this product is in the kernel of this map because this relation doesn't hold in the Cactus group. And that's actually the only thing in the kernel, well, I mean, generates the kernel. So the kernel in this case just said. So the Cactus group is meant to remind you of another group which maps the symmetric group called the braid group. So the braid group, I just put it up here just for comparison. So it has less generators than the Cactus group. So in that way, it's kind of simpler. On the other hand, its generators don't square to the identity. So in that way, it's more complicated. But and its relations are, well, a little bit of a different nature. There's a similar thing that faraway generators commute, like this relation. And then there's another relation which is not exactly like this relation, which is this kind of, well, related to this picture, this Radameister 3 kind of picture. So the Cactus group and the braid group have a lot of features in common. We'll see a little bit of that soon. So one thing about the braid group, well, you can also consider the pure braid group, which is the kernel of the map from the braid group to the symmetric group. And that pure braid group is the fundamental group of a nice space. Just take C to the n minus the diagonal. So which is just a configuration of n points in the complex numbers, not modulo of some group, but that doesn't matter too much. Okay, so natural to expect that our Cactus group is also a fundamental group of something. And in fact, there's the theorem of Davis, Januszkiewicz, and Scott. And as Jacques said, here's the idea behind it. So let me draw a picture since it's easier to understand when the things are drawn because you see what's happening. So first of all, the statement is that the pure Cactus group is the fundamental group of the moduli space, Mn, the one I started talking about. So an element in the Cactus group corresponds to a path in the moduli space, but that path doesn't come back to where you started unless you're in the pure Cactus group. So I'm going to explain how to associate paths in the moduli space to generators of the Cactus group. So I need a path for the element Sij in the Cactus group. And what does that path look like? So I take my point in the moduli space. Let's say it's in the open part of the moduli space, so where I have n plus 1 distinct points. And I look at the points between the I and j, and I'm going to make those points all sort of simultaneously come together, and the other ones come together in their own way, so that these points between I and j head off onto their own component. And then I reach a point in the moduli space which has corresponds to a 2-component curve, like so, where the points from I and j are on that component, and the rest of the points on the other component. And as I said a few times, one thing we have is this -1 element in the automorphism group of P1, and that comes into play. Once these guys have gone off on their own component, you can't tell the difference between this ordering and the ordering where it's flipped. So this point is actually the same point as the point where this component, where the original component has sort of been unchanged, and this component has flipped. So then, once we've realized that, then we go back to a different point in this open locus of distinct points, where now we've switched the orders as so. So altogether, this thing is a path in the moduli space Mn. So I went from one point in the moduli space through this special point, which is kind of on the boundary of the moduli space, and back into this other generic kind of point of the moduli space. And that path is where Sij goes to. So then if you concatenate a bunch of paths, if it goes to the identity in the symmetric group, you'll be back to where you started on here. And so you get a loop in the moduli space, and that's the isomorphism. And another thing which Davis, Januszkiewicz, and Scott proved is that the higher homotopy groups of the moduli space vanish. It's not very important for our purposes today. But it shows, well, maybe what it shows you is that that Mn and the Cactus group are very naturally linked for that reason. Mn is what's called a K-pi1 space for the Cactus group. I mentioned that the Cactus group and braid group were closely linked. So one important feature of the braid group in representation theory is that the braid group acts on representations of Lie algebras. And this action is very important because it leads to what's called quantum non-variance, such as the Jones polynomial. Let me just briefly explain how this works. So suppose I have a semi-simple Lie algebra, for example, like SLN, or even more specifically SL2, and I have a bunch of representations, n representations of that semi-simple Lie algebra. Then the braid group will act on the tensor product of those representations. And there's actually two ways of defining this action. Neither of which is like totally straightforward, because the action is not so straightforward, right? Like if you have some tensor product, you might expect like the symmetric group will act like permuting the tensor factors. That would be sort of a simple kind of action, but we're upgrading that kind of to this braid group action, so a more complicated thing. So the construction is going to be a little bit involved. So there's two definitions for this action. One, you deform the semi-simple Lie algebra to this more complicated thing called a quantum group. And quantum group has basically the same representation theory. So this V1 tensor Vn is still a representation of the quantum group. But the quantum group comes with what's called an R matrix. And this R matrix allows the braid group to act. So the braid group generators act using this R matrix. That's the first approach. And the second approach is more geometric. There's a way of defining a flat connection on the trivial vector bundle whose fiber is this tensor product. So it's a flat vector bundle over Cn minus delta. And when you have a vector bundle with a flat connection, the fundamental group of the space acts by monodromy. So the braid group is the fundamental group of this Cn minus delta, and will act by monodromy. So this connection is called the Examlogical connection, and it's given by some formula, which I don't want to recall.
So the VI aren't necessarily isomorphic.
Yeah, technically, if they're not the same, if they were different representations of braid group, it wouldn't really act on this tensor product because it would switch them around. Like technically, only the pure braid group would act. So to be slightly more precise, yes, I should have either written the pure braid group acts on the tensor product, or I should have written the braid group acts on the tensor product of a bunch of copies of the same representation. Yeah. So this would be a little bit more correct, but ignore this problem. And a celebrated theorem of Drinfeld and Kono says that these two actions of the braid group are the same. So we're going to see now some Okay, so I'll begin with the following theorem, which I guess originally maybe some version of it due to Berenstein and Kirillov, and then later myself and Andre Henriquez, states that this Cactus Group, and this is like the reason for my interest in the Cactus Group to begin with, since I don't just go randomly investigate finally presented groups. So my interest in this Cactus Group to begin with is that this Cactus Group has a habit of acting on combinatorial objects that appear in representation theory. So what do I mean by that? Well, I give sort of two flavors of it. So let me start with the first one. So the first one is that if we take what's called the semi-standard Young tableau of a, say, shape lambda. So lambda here is some partition, so usually drawn as a Young diagram, like so. And then this semi-standard Young tableau, this means fillings lambda by 1 up to n, and they should be weakly increasing in rows and strictly increasing in columns. So for example, you could fill it with 1, 1, 3, 4, 5. So that would be a possible element in this set. And this semi-standard tableau is a very important object of study in algebraic combinatorics and in combinatorics. So this is one thing that the Cactus Group acts on. And maybe in this form is sort of was the form of Berenstein-Kirillov. And more generally, it acts on something called a tensor product of crystals. So I mentioned that this, we have semi-simple Lie algebras and we have their representations. We can take their tensor product. There's a kind of combinatorial version of that story where these representations are replaced by, so here we had representations of some semi-simple Lie algebra, V, and these representations are replaced by something, a combinatorial object called a crystal. So for example, when G is equal to SLN, this combinatorial object is precisely this set of semi-standard Young tableau. And then we, just like here, we considered, say, some tensor product of these representations. Here we could consider some tensor product of these crystals. And the Cactus Group acts on such things. So just like the braid group acted here, oops, yeah, too many B's. Anyway, this is the braid group. So here we have the braid group, and here we're going to have the Cactus Group. So in a little later, I was going to give an example of this kind of action. But for now, let's just take it on faith that there's this kind of combinatorially defined action. So this is just defined purely combinatorially. So like I take each generator and I say how it acts on this tensor product in some combinatorial way. So we kind of view this as like, if we go back up slightly to this Drinfeld-Kono thing, I mentioned two ways the braid group acts. This is kind of like number one. So now we're going to ask, what's the analog of number two? So like, what is this? In other words, what does this action have to do with this moduli space that we start? To answer this question, we're going to use this construction from mathematical physics called the Godam model. So let's begin as follows. So let's take the Lie algebra SL2. So a specialized SL2 here just for simplicity. But what I'll say will work for any semi-simple Lie algebra. And I take n representations. So people were interested in, well, people are of course interested in these tensor products. From the viewpoint of physics, these are like sort of like n elementary particles, and this SL2 representation has to do with their spins. And people are just, so this guy Gaudin, 50 years ago, he wrote down these Gaudin Hamiltonians, and they're given by the following formula. So I is fixed, and we vary J. And then we have this sigma ij over Zi minus Zj. So what does it mean? So sigma is the Casimir element of SL2. So I give the formula for it over there. And then this ij means that I act on just on the I and j tensor factors. So these are some operators, and they depend on parameters z, which are used in the numerator here. So the z's are just some real numbers. Of course, for this numerator to make sense, we better have zi not equal to zj. Okay, so what's good about these Gaudin Hamiltonians? So the first fact is that they commute among each other. But when I say that, I mean that when I is not J, but the Z's are the same, they commute. HI of Z and H, so like, for example, H1 of Z and H2 of Z commute. Another thing which is good about them is that they're Hermitian operators. So on these SL2 representations or on representations of any semi-simple Lie algebra, there's a natural Hermitian inner product, and these guys are self-adjoint with respect to that Hermitian inner product. So in other words, each of them is diagonalizable. So they're each diagonalizable because they're Hermitian. And in fact, because they commute with each other, they're in fact simultaneously diagonalizable. So we can take the whole collection of them and simultaneously diagonalize them. They're acting on this big vector space here, this tensor product. And so we can find an eigenbasis of vectors, which are eigenvectors for all of these guys. And then the next point, number 2, is that they have a simple joint spectrum, so that those eigenvalues will be different for each of those different eigenvectors. So it's not quite true because these operators, another special feature of them is they commute with the action of SL2. So what's really true is that they have a simple joint spectrum on the tensor product multiplicity spaces. So not quite on this space, but if we were to take, say, of SL2 from some other representation into this tensor product, where all these guys are irreducibles. Actually, on this tensor product multiplicity space. So on that space, they would have this simple joint spectrum. So, I mean, like, why would people be interested in this? Maybe because people are interested in studying this tensor product and understanding how it decomposes into irreducible representations. And one way to study that is to study these tensor product multiplicity spaces. And how are you going to study this vector space as tensor product multiplicity space? Well, one way to study it is to find these operators and decompose it into eigenvectors for these operators. So that's sort of points 1 and 2 of this theorem. And by the way, I didn't really say this at the beginning, but this theorem is the work of many people, not like including, but maybe not limited to the ones I listed here: Fagan, Frenkel, Rybnikov, and Aguirre, Felder, Veselov. And I didn't even mention, Gaudin and all the other people probably who worked on it. Now let me come to number 3. So this operator is dependent on this parameter z, which I didn't say much about. So I had these n real numbers. They appear in the denominators here. And of course, if you scale the z's, it's only going to change this whole thing by a scalar. And if you translate the z's, it's not going to affect anything because we have their differences here. So the algebra, I can look at the algebra generated by these n operators. I can consider a map from Z, take the Z and produce the algebra generated by these n operators. And so this Z was an element of Rn minus delta, and it's not going to depend on the Z's, on the image will be well defined if I translate or scale my Z's. And of course, we saw this Rn minus delta by the translation and scaling at the beginning of the talk. So it's natural to think, well, that we have this nice compactification of this space. And it's so, on the other hand, if you think about these space of operators, they also sort of, you can take limits in that space of operators. And it's so that what you would expect is that, or what you might hope, is that this map here extends to a map from this moduli space to this subalgebras.
So where's the scale invariance?
Well, it'll just scale. If you scale them, it'll just give an overall scale to this thing. So the subalgebra they generate will be invariant.
Oh, I see. Oh, it's the sub. Okay, sorry. Yeah.
So each operator won't be invariant, but the subalgebra they generate. And so it extends. So I mean, not obvious fact. And even though this Gaudin stuff was from 50 years ago or more, this thing was only proved, I don't know, 10 years ago somehow, that that it actually extends from that from this moduli space to the space of subalgebras. Maybe it was known before in different ways, but only really in this language proven like that recently. And again, this works for any semi-simple Lie algebra. If we work with other semi-simple Lie algebras, there's still these Gaudin Hamiltonians defined by the same formula, but there are not enough of them. They don't have a simple joint spectrum. So you have to add these higher Godin Hamiltonians. The story is much more complicated, but it works fine. The theorem is still true. So what does this mean? So now for every point in my moduli space, I have a subalgebra of this tensor product. So for every point in my moduli space, I can take a look at the eigenlines, so eigenvectors, but to not have to choose the scalars, I just say eigenlines. Eigenlines for the action of that corresponding algebra, subalgebras of, oops, not of V1 tensor, but of the endomorphisms, obviously. Subalgebras of that thing. So when my Z was one of my original points corresponding to these distinct numbers, then I'm just looking at the simultaneous eigenspace of these n operators. And more generally, I'm looking at the limit subalgebra, the simultaneous eigenspaces for everything in that limit subalgebra. And because those subalgebras of this endomorphism algebra, because they're varying nicely as I move around in my parameter space, their eigenlines will move around, will vary nicely, and I get a topological covering space, but like a covering space where the fibers are finite, right? Because the fiber consists of a bunch of lines in my vector space, so finite set. So the size of the fiber is just the dimension of this V1 tensor Vn. And technically, I should not work with V1 tensor n. I should work with these tensor product multiplicity spaces, but I left it as V1 tensor Vn to avoid complicating the notation. So in this way, I get a covering space of my moduli space where the size of the fibers is the dimension of V1 tensor Vn. And so it's an interesting question to understand the monodromy of that covering space. So it's a topological covering space. So the fundamental group acts on any particular fiber.
It's a sort of spectral cover.
Yeah, exactly.
Okay.
It's exactly. Yeah. And so our theorem from a couple of years ago, this with Eva Hlacheva, myself, Lenny Ribnikov, and Alex Weeks. So it states that the monodromy of the covering is given by this combinatorial action that I mentioned earlier. So the action on the corresponding crystal. So there's a sort of natural corresponding combinatorics, and that acts. So there was what's nice about this description or this theorem is that the originally when I define I have two. So I have two approaches: combinatorial approach and this business with the subalgebras. So the subalgebras, it just has to do with the moduli space and the fundamental group, and the other side has to do with the purely combinatorics and the Cactus Group. Okay, so there are two approaches, and they're linked by this theorem. So I just wanted to give one kind of example of this action before continuing, because it was a little mysterious. I didn't really say how this combinatorial action works. So here's an example. So today I take, it's kind of the simplest example, but still highly non-trivial. So say I take G to be SL2, and I take a whole bunch of tensor products of C2, and 2n of them. And inside there, I look at the invariance for the action of SL2. So this space invariance is like a very nice studied thing. And its dimension is given by the Catalan number, 1 over n plus 1, 2 inches, 2 inches n. In this Catalan number is a count of many nice combinatorial objects. So the combinatorial object I'll consider here is what's called ballot sequences of length 2n. So imagine you're having like a referendum, and then so some people are voting with plus and some people are voting with minus, and the referendum ends up in exact tie, but the entire time you're counting the vote, the plus side is always winning, or tied. So the partial sums are always positive. I don't know which side is the plus side, which side is the minus side, but so so these are called ballot sequences of length 2n, and it's well known that the number of them is given by this Catalan number. And there's well, somehow since I just reminded of it since my picture, there's lots of other nice combinatorics, for example. So also you could think of it as some kind of diagram, cup diagrams like this. You can think of it as balanced parentheses, like so. But the plus and minuses are maybe easier to draw. Okay. So let me explain how this Cactus Group acts on these ballot sequences. So you take one of these ballot sequences. Maybe I'll do a slightly different example than the one that's there. It's too long, but okay. 1, 2, 3, 4, 5 minuses, 5 pluses looks good. Okay. So then you take your cactus group and it decides to grab a section of this thing. So whatever cactus group element it is. So this one would be S2. So it starts at the 2, 3, 4, 5, 6, 7, 8. S2, 8 acts on that section. And the action of this cactus group does 3 things, surprisingly. Its first step, first of all, it doesn't do it. It never does anything to the things outside the range. So its first step is to switch all the pluses and minuses. It switches completely the voting. Of course, it's not a ballot sequence anymore because it's now the minuses might be winning at some point. So you switch all the pluses and minuses. And then it's, oh, I guess even worse now, the minuses are overall winning. The next step is to switch plus minus. Just highlight the range we're still working in. The next step is to completely reverse the order of that thing. So minus, plus, minus, minus, plus, plus, minus, minus, plus, minus, minus, plus, plus, minus. Okay. So I just, if I don't make a mistake, I just switch the order in this section, or reverse the order. And then the next step is like a slightly harder to explain. I call it Schützenbergian evolution. So what it means is, here's the best way of thinking about it. And listen, so let's turn it into the other model where I have brackets, but only in that section. So here I have some brackets. So if I then look at my brackets, I match up the ones I can match up. So this one I match up and this one I match up. Ignore those for a second. Now I have 2 of these opens, 2 of these ones and 1 of these ones. So I'm going to switch it. So I want to instead have 1 of these ones and 2 of these ones, but in kind of the same order. And I keep these guys where they were. Okay. So there was, so just to see what happened, there was 2 of these guys and 1 of these guys. Now there's 1 of these guys and 2 of these guys. And then I can convert back into the brackets and I get back to a ballot sequence like so. So that's the last step. I don't know, that's the complicated step. So so again, this was the action of the cactus group of size 2n on these ballot sequences of length 2n. And these ballot sequences of length 2n, it's the combinatorial model for this tensor product C2, tensor 2n, SL2 invariance. Now I'll just briefly outline our more recent work, which is a kind of a generalization or extension of these results. So the reason somehow why I decided to give this talk today is because recently we've been working on it. It's like not worth talking about the new results in great detail, but just I'll just mention how it gets extended. So I didn't really call it that, but those algebras that I mentioned before are called Gaudin algebras, the ones generated by those Gaudin Hamiltonians. And there are some natural generalizations of these Gaudin algebras called inhomogeneous Gaudin algebras and some other ones called trigonometric Gaudin algebras. One reason why we're interested in these other versions is these trigonometric Gaudin algebras appear as a quantum cohomology of certain natural spaces called affine Grassmannian slices. So because they appear as these quantum cohomology algebras, that's one motivation to study them. So that's the generalization of the algebra side. On the moduli space side, rather than studying a compactification, so of R, so I started by thinking about Rn mod R or Rn mod, well, so at the beginning of the talk, I was talking about compactifying Rn mod scaling and translation. It turns out that, well, in other words, maybe to make it look more similar, I could write this as R cross minus delta mod R cross. So I throw away 0 using the translation. I get rid of the 0. So now it looks sort of more like this. And now what I'm going to do is I turn from R cross to the unit circle. So unit 1 complex numbers. So U1 then minus 1 minus delta mod U1. So my new space that I'm studying is a compactification of this. So rather than compactify this, I compactify points on the unit circle. So that's the space, and that's one of the two spaces. Somehow that's the one related to the trigonometric Godin algebras. And there's another space which is related to inhomogeneous algebras, which is called a FNR. I don't know. I don't have time to explain it, but here's a little picture of the space. One feature you see is that there's a very special point that many of these guys are allowed to meet there. And finally, this Cactus group, which I explained the definition of, which appeared as the fundamental group of my modular space, it's going to be replaced by something called an affine Cactus group. Affine here refers to sort of affine Lie algebras or affine Dynkin diagrams. So it ends up meaning that rather than the intervals along a circle, the generators of this affine Cactus group have to do with intervals on a circle. Sorry, I don't know if I said that right, but before we had intervals, we were considering like 1 up to n, 1, 2, and so on, n minus 1, and the generators had to do with intervals in here. And now now I'm going to consider n points on a circle, and the generators will have to do with intervals in here. So it turns out you can use exactly the same definition, but applied to intervals along a circle, with the same kind of rules about intervals being contained in each other and so on. And you get a different group called the affine Cactus group. And that's the one which appears in this story that I didn't explain. That's all. Thank you.
Thank you.
Does anyone have any questions in the online?
Joel, I actually have a question. What did you say is the name of this this flat connection on the trivial vector bundle over Mn?
It's called the Examlogical connection. It's very hard to spell, but I can try. Like so, I think. Uh-oh.
Kira, do you want to type it into the chat?
That's probably not right, but
I'll put it in the chat.
Can you see it?
Yeah, I can.
people usually call it like KZ connection.
Okay.
For obvious reasons.
Oh my God.
Actually, well, it's not. In some ways, it's actually almost appeared on the board here. These Godin Hamiltonians are basically the right-hand side of the Examlogical connection. So the connection looks something like del Zi plus Hi. That's actually the formula for the connection.
Uh-huh.
There's a classical Godam model that comes up in integrable systems.
Is it related? I mean, I assume it's the same
It must
thing.
be.
Does it not look like that? I don't know much about.
So I mean, it's going from going from symplectic or Poisson manifolds to quantum things.
Yeah.
It's got a spectral curve. It's very nice and very easy to. And also, I presume you have. I mean, your pictures suggest there must be one of these Cactus groups for any simply laced Dynkin diagram.
Yeah, there's a parallel of this. So these Cactus groups in this moduli space are associated sort of to SLN, and there's moduli space and Cactus groups associated to any simply laced Dynkin diagram. And in fact, there's like two combinatorial actions of the Cactus group. The one sort of permuting the tensor factors, and a one kind of internal action on the crystals of that type. If you took tensor products of any semi-simple Lie algebra, this Cactus group that I mentioned will act by permuting the tensor factors, but on any particular one, this internal Cactus group will act. It's similar to the story about braid groups. There's braid groups of any type as well, which behave the same way with spectral representation.
And then I had another question, which is that you're looking at the real moduli space of curve. Now, this isn't the only real moduli space of curves, because one of the natural things to do would be to sort of put involutions and fixed points under involutions. So you have a complex objects, and you look at configurations of points that are invariant. So you could get pairs, conjugate pairs, for example. So it's a different, a bigger space. Does it have any use, or I mean, it's like the roots of a real polynomial, basically. I mean, that's the.
Yeah. Well, I would say the following: if you fix any, if you take 1 up to n, and you fix any sigma involution on 1 up to n, sigma squared of Zn, and then you can consider curves, complex curves, with marked points, and such that the complex conjugate of Zi is Z sigma of I. And this will be a real form of the complex modular space.
Yeah.
But you'll get a different real form for every sigma. So what we were studying today was where the sigma is just the identity.
Yeah.
So there's lots of these different real forms around, and they all have fundamental groups. And actually, this was studied by Özgür Seyhan. And actually, this space, the one I mentioned somehow toward the end here, having to do with this trigonometric Godin algebras, that actually turns out to be the case, the same one of these spaces for the special case when sigma has the following form, like sigma of 1 is 2, and sigma of 2 is 1, and sigma of I is I for the rest of it. So this is like the next most simplest case you can imagine. So it just switches two things and the rest is identity. So this one, the fundamental group of this moduli space is this affine Cactus group. And I don't know, I don't know a nice description of the fundamental groups of these other spaces. I don't know any natural way in which they arise, but this one happens to arise in a natural way. So it's possible that these other ones might be interesting too.
Of course, sorry, they all mix together, I guess, when the points are unordered. That's sorry, so it's getting a little bit. Any other questions? Or?
Let me
try. Go ahead, Franco.
No, please, Ivan. All right, so I'll ask quickly. These operators, the Gaudin operators, you said they have simple spectra. Do we know what the eigenvalues are? And how do they kind of vary when you extend your map to Mn?
Well, in some sense, the way that the eigenvalues are varying is this monodromy. I mean, like as you move through a path in Mn, and you come back to where you started, what's happening to those eigenvalues is given by this Cactus group action on the crystal. Somehow that's our theorem. It tells you exactly that's how the eigenvalues are varying. I mean, a slightly different question is, what exactly are the eigenvalues? Like what, numbers are they? That's actually an interesting question too. In fact, there's this work of Mukhin, Asov, and Varchenko, which directly relates these eigenvalues to Schubert calculus. So solutions of Schubert problems. So real Schubert calculus means studying certain configurations of flags in vector space. So they're directly related, these eigenvalues, to these configurations of flags. And in this, I guess this is only true for SLN. But for SLN, there is this connection to this Schubert calculus, and so our theorem that I mentioned about relating the monodromy to the action on the crystals, using this connection, the theorem can be proven using work of David Spire and Kevin Prabhu and Noah White. So if you combine together their work, which is sort of on this Schubert calculus side, then it's an alternate way of thinking about the theorem I mentioned.
Thank you. That's a very detailed answer.
Maybe I'll pick up from where Franco left. So the Gaudin's operator, they commute when evaluated at the same Z. So actually, if you take the simplest case of SL2 and all the two-dimensional, the C2 module that you've taken, but not necessarily 2n, but n, the endomorphism should be the temporally Lieb algebra, correct?
That's right, yeah.
But so the Gaudin map take a point Z and sends it to a abelian subalgebra. So it's a abelian subalgebra of the temporally Lieb.
That's right, yeah.
Okay, so I wanted to check. So the center of the temporally Lieb is known. So we know pretty much what type of algebra the Gaudin operators can reach within the endomorphism algebra.
But it's not central. I mean, the image won't be in the center of the temporally Lieb algebra.
It won't be only abelian, but you don't get much of the temporally Lieb algebra, right? Or if you change the point Z, can you manage to reproduce the whole endomorphism algebra?
I'm pretty sure that if you took all the operators you get for all z's, then you would generate the whole algebra. Maybe I don't know exact proof of that fact, but I think it sounds, But yeah, for any fixed z, you just get this commutative subalgebra, but it's a maximal commutative subalgebra of that. It's actually an interesting question. How do these operators look inside the temporary leaf generators? I don't know the answer to that question, but it probably isn't that hard to figure out.
And there's no Q. I mean, it's the temporally Lie algebra, or it would be the heck the group algebra of Sn essentially with a quotient. But can you do? They form the structure with a Q to get the information for the tensor product of UQ SL2 modules?
Yeah, that's a good question. I don't know the answer to that question, but it's a good question. I think there was some work done about this kind of thing, but I don't know. Yeah, I'll stop here.
Thank you very much. It was great talk.
Thank you.
Questions? If not, well, thanks again. And thank you for a very good talk.
Thank you, Joel.